All right, hi everybody. So today we're going to learn to draw Lewis structures for the formation of ionic compounds. So ionic compounds, remember, are those with an electronegativity difference of greater than 1.7. So you have one atom that really wants the electrons and the other that doesn't really want them very much at all. And so you wind up with a positive ion called a cation, that being the atom with the lower electronegativity that loses its electrons. Usually that is a metal. And you have a negative ion called an anion, that being the nonmetal that has a higher electronegativity and gains the electrons. So we'll start off with a relatively easy one. We're going to do one between, let's say, lithium and fluorine. So Li, and I'll use different color for this one, and F. So the first thing we are going to do is draw the Lewis structures themselves. And so as you see, I've started by writing the element symbols. And now I'm going to figure out how many valence electrons each of them has. So let's start with lithium. I'm having trouble switching between colors. All right, we'll start with lithium. And if we look at our periodic table, remember we figure out valence electrons by counting spots over from the left. And lithium's in the first column here. So lithium has only one valence electron. So its original Lewis structure is just going to have one dot right on top like that. My brush size up just a little. Okay, so lithium's going to have one valence electron. Fluorine, on the other hand, is all the way over here. So it's 1, 2, 3, 4, 5, 6, 7. 7 spots in, so it has 7 valence electrons. When I draw those, I'm going to draw the first two on the top, 1, 2, and then I'm going to start on the 3 other sides, so left, bottom, and then right, and I'm going to go 4, 5, 6, 3, 4, 5, this is 6, and that's 7. So I have 7 dots around fluorine. The first two go on the top, and then I put 1 on each side. Once the 3 sides have 1 each, I start filling up again. And so if we look at our electronegativity values here, I did this by going to our P table, clicking on properties, and then selecting electronegativity as our little button there. And the electronegativities show up in the bottom on the squares themselves. Notice for hydrogen it's 2.2. If you blow hydrogen up like this, it gives you the atomic number and atomic mass, but we want to use the number from the table itself, which for hydrogen is 2.2. So we wanted to look at the electronegativity for lithium, which is, we're going to round that up to 1.0. And the electronegativity for fluorine, which will round up to 4.0. So the difference there is 3. 4 minus 1 is 3. And so that's definitely an ionic compound. That's very ionic. So fluorine, having a higher electronegativity, is going to take lithium's electron. To show that happening, we're going to draw an arrow from this electron on lithium to what we'd consider kind of the empty spot on fluorine, because it can hold up to 8 to fulfill that octet rule. And it's, so you think of it like it can hold 2 on each side. So its empty spot is on that one side that doesn't have any anymore. Now I'm going to redraw the fully formed bond here, and I'm going to do that in brackets. So I have Li, and lithium lost its valence electrons, so I'm not going to draw any electrons around it now. I mean, because it lost this one that it had. And I'm going to draw a plus sign to show that lithium lost that 1 electron, so now it has a charge of +1. For fluorine, on the other hand, I'm going to draw it with all those valence electrons. So it has 1, 2, 3, 4, 5, 6, 7 of its own, and it has the one that it took from lithium. So I'm going to draw that in there as well. Because it gained an electron, it started out neutral and gained an electron, it's negative. So I'm going to put a negative sign up there. And this is my completed Lewis structure for the compound is called lithium fluoride. So it's an Li, 1 Li and 1 F. If I look at the oxidation numbers for lithium and fluoride, lithium and fluorine, lithium's, you can see in the top right here, is +1. Oh, lots of things highlighted there. And then fluorine over here is -1. And those are the charges that they wound up with, which is good. So that's how we can tell we did the right thing, is if they have the charges that their oxidation number says they should have. Now let's do one between let's try beryllium and chlorine. So we have beryllium right here, atomic number 4, and chlorine over here, atomic number 17. So with our nonmetals, which are our anions, we're always going to use the top oxidation number, so it's -1 for chlorine, and beryllium is going to have a +2. So if I go back over here, I'm going to draw beryllium. I'll do that in pinkish. And chlorine is going to get this kind of purpley color. Chlorine. And so if I look at our valence electrons here, chlorine is 1, 2, 3, 4, 5, 6, 7 spots in. So it's going to get 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And beryllium is only the second spot in, 1, 2. So beryllium is going to get 2 valence electrons, and remember those are both going to go on top of it. So I'm going to get my color here, like that. Okay, so chlorine has an oxidation number of -1. I'm going to write this in a little bit smaller of a size over here. So chlorine is going to be -1. And beryllium wants to be +2. So if I were to just give chlorine one of these electrons right now, because to fulfill its octet, it can only accept 1 in this empty spot right here. That would fulfill chlorine's oxidation number. Chlorine would have gained 1 electron and become -1. But beryllium would have only lost 1 electron, so beryllium would be +1. It would have this other valence electron right here that it doesn't really know what to do with. So it needs to get rid of that as well. And so the way we can deal with this is by having 2 chlorines. And we can figure out that we would need that by crossing the oxidation numbers. So if I show you, so we have, oh my goodness, we have our oxidation numbers written the way they are right now. We're going to need 1 beryllium, this one beryllium, for every 2 chlorine. So we're just kind of crossing the numbers. We need 2 chlorine and 1 beryllium. So if I draw myself another chlorine over here with 1, 2, 3, 4, 5, 6, 7 valence electrons, and then I draw an arrow going from beryllium's other electron down there, now I've got this beryllium has lost both of its valence electrons, so that's good. It's +2 now. And chlorine, each of these chlorines has gained 1, so they're each -1, which is the oxidation number that we wanted. So when we go to rewrite this, we're going to draw beryllium with no valence electrons around it. And it's going to have a charge of +2 because it lost 2 valence electrons. And then each of my chlorines, I'm going to draw one over here, and it's going to have 1, 2, 3, 4, 5, 6, 7 of its own, and 1 from beryllium, and its charge is -1 because it gained 1 electron, and over here it should be right next to it, but I'm going to go down just a little bit. Chlorine has 1, 2, 3, 4, 5, 6, 7 of its own, and 1 from beryllium. And just like before, we close it off and give it a -1 charge. So the formula here would be BeCl2 because we have 1 beryllium and 2 chlorine, and each of them has the oxidation number that it wants. Alright, we'll do one more example of Lewis structures for ionic compounds. This time we're going to do it between aluminum and, let's go with, aluminum and bromine. Let's do bromine. Just to mix it up a little bit. Get bored of our halogens here. Bromine. So, actually, I don't want to do bromine. Let's do aluminum and oxygen. I think that's a better idea. I'm going to show you something different. Aluminum and oxygen. So aluminum, we can look at our periodic table here and see that it has 1, 2, 3 valence electrons. So when I draw that, aluminum is going to get 1, 2, 3 valence electrons, and oxygen should get 6 because it's 1, 2, 3, 4, 5, 6. So we're going to go 1, 2, 3, 4, 5, 6. If we look at our oxidation numbers, we see that aluminum has an oxidation number of +3 and oxygen has an oxidation number of -2. So we have aluminum is +3 and oxygen is -2. So what this tells me is that I'm going to need 2 aluminum atoms and 3 oxygen atoms. So if you see, I'm crossing the elements and their oxidation numbers, and that tells me how many of each I'm going to need. So if I need 3 oxygen, I'm just going to draw them one right above the other here. 3 oxygens, and they each have 6 valence electrons. And then I need 2 aluminums. So here's another aluminum. Alright, so I've got the number of atoms that I should need in order to make this work, and let's see if it does. So basically, you can see that each oxygen has 2 empty spots on it because it has 6 valence electrons and it needs to wind up with 8. So I'm going to draw an arrow going here and an arrow going down there. So I got rid of 2 from that aluminum. I'm going to take 1 from here and put it there, 1 from here and put it down there. And I've got 2 left. This one's going to go here, and that one's going to go there. So there's a lot of electrons moving around. There's a lot of moving parts here, but you can see that by the end of it, these 2 aluminums have gotten rid of all of their valence electrons, and each of these oxygens has wound up with a complete octet. So that's good. So when I redraw it, I'm not so much worried about the shape of this. I'm going to do aluminum. No valence electrons are on it, and it's +3. And I want to kind of show that they're attracted to each other because they're positive and negative. So let's do an oxygen next to that. Oxygen, it has 6 of its own and 2 from aluminum. And if oxygen gained 2 electrons, it's -2. I have another aluminum over here, no valence electrons, and it's +3. And we'll do another oxygen over here with 1, 2, 3, 4, 5, 6 of its own valence electrons. I'll finish that off in a sec, and we'll do another one over here with 1, 2, 3, 4, 5, 6 of its own valence electrons. They each gained 2 from the aluminums, and their charges are going to be -2. This also works out because you should always be able to add up all your charges and get 0. So if we have +3 and +3, that gives us +6, and -2 plus -2 plus -2 gives us -6. And so we add that up, and it's 0 because we started out with 5 neutral atoms. So we shouldn't wind up with something that's charged. Our final product should be neutral if all of the things that went into it are neutral, because we didn't add or subtract any protons or electrons. We just rearranged them. So that is how you do Lewis structures for ionic compounds. It's going to be different when we do it for covalent. Next thing I'm going to upload will be a video of how to name ionic compounds. Hope this helps. Bye.